Welcome back everyone. In this lecture, so we will prove that the map that we defined in the earlier lecture var phi is actually injective map. So let me recall what is the map. So basically given finite dimensional semi-simple Lie algebra, we have chosen some maximal toral subalgebra and then got this root system. So that is what the map var phi is all about. So let me recall what very explicitly what is this. So you take this set of all isomorphism classes of finite dimensional semi-simple Lie algebras. So from this set you actually define a map var phi, which is target spaces again set of all isomorphism classes of finite root systems. The map is simply you take G and then associate with its root system phi. So how we make this choice? So given G, you fix some maximal toral subalgebra. So then with respect to this pair, we have the root space decomposition by acting this H on G via H joint action. So then you get H direct sum G alpha alpha in phi. So then use this root space decomposition and then get the set of roots phi. So that is the map. So what we want to prove that this map var phi is actually injective. That means if there are two root system coming from two semi-simple Lie algebras G G dash. So suppose these two root systems phi and phi dash, they are isomorphic. So then we want to prove that the respective semi-simple Lie algebras, they are also isomorphic. Okay. So before proving that, so let's understand something about this map. Okay. So for example, we have the notion of simple Lie algebras on the left hand side, and then we have the notion of irreducible root systems on the right side. So we also have simple ideal decomposition of G, and then we also have irreducible root system decomposition of this phi. Okay. So we want to compare all these things. So on the left hand side, we know that G can be written as G1 direct sum etc. GT, where each Gi is simple ideal inside. On the right hand side, we have this irreducible decomposition of phi. So you can write phi as direct sum of these irreducible root systems, irreducible decomposition of root system phi. So that means each phi I is irreducible inside phi. Okay. So we want to actually compare these two decomposition and then see so what corresponds to what. So it's easy to guess what one expects. Actually, if you start with a simple ideal decomposition of G, then that should corresponds to irreducible decomposition of phi. So basically what we want to prove, again this is a theorem, but easy theorem. If you write G as G1 direct sum etc. direct sum GT, so with each Gi is simple ideal inside G. So then what one can actually see, you have this maximal toral subalgebra inside G. So you have this maximal toral subalgebra So, then with respect to that you have root system phi, let us say. So, phi is the root system of this pair G and H. So, now we want to understand how this phi behaves with respect to this simple ideal decomposition. So, as expected what one can actually get. So, we can prove that in this case if you take H I, which is the intersection of H with G I. So, that will be maximal toral subalgebra of G I, and then you can talk about root system of this pair G I H I. So, let us call this phi I is the root system of this pair G I and H I. So, then what one can do, one can naturally identify phi I inside phi. Okay. So, there is a natural way of identifying phi I inside phi, and so this is done via you take alpha in phi I and then define alpha, which is again we call it alpha, which is from H to C such a way that alpha restricted to H I is just alpha, and then alpha restricted to H j is 0 for all I, for all j not equal to I. So, basically you trivially extend alpha to H, so that you get map, you get an element alpha in H star. But what one can prove? One can prove that this alpha must be inside phi. Okay, this is part of the proof. So, then what we have, we can write phi as disjoint union of all this phi 1 etcetera phi t, and not only that, if you take alpha beta from different components, then the inner product will be 0. So, if alpha is from phi 1 phi I and then beta is from phi j where I not equal to j. So, then you can have that alpha beta is actually 0. Basically what we are saying, if you take H to be a maximal subalgebra of G and then phi is the root system associated with this pair G H, then if you can write G as direct sum of simple ideals, then we will be able to produce maximal toral subalgebras of GIs. So, which will be just H intersection GI, and then if phi I is the root system of GI HI pair. So, then phi can be written as direct sum of irreducible root system with respect to these pairs GIV HI. And you can see that conversely, if phi is actually coming from if it is a root system of some pair GH, and phi if you write it as direct sum of irreducible root systems phi 1 etcetera phi t. So, then you can prove that easily G can be written as direct sum of the simple ideals GI. Okay. So, in particularly in this association that we have sending G to phi, the simple Lie algebras are mapped to irreducible root systems. So, actually only the statement is important. Okay. So, the proof is not that hard to actually verify. So, maybe I will leave it to you to just check. So, at this point you should be comfortable enough to check whatever stated in this theorem. Okay. So, I will leave it as exercise to check this result. So, what indeed we are saying with this map var phi, simple Lie algebras are mapped irreducible root systems, and if you write G as G1 direct sum etc., direct sum GT, which is direct sum of simple ideals. So, that corresponds to irreducible decomposition of phi. So, phi is written as phi 1 direct sum etc., direct sum phi t, where phi i's are irreducible. So, this is the correspondence that we are talking about. So, now this indeed actually reduces our work when we want to say that phi is injective. Okay, to prove phi is injective, so it is enough to assume phi is actually just irreducible root system, okay, or G is simply algebra. So, otherwise what happens, you can actually write phi and phi dash as direct sum of irreducible root systems, and then you can see that if phi is isomorphic to phi dash, then the corresponding irreducible components will be just permuted. Okay. They will be, what I mean by that, they will be isomorphic to each other. So, let me just write it what I want to say. If phi is isomorphic to phi dash, and then if you write phi as phi 1 direct sum etc., direct sum phi t. So, then you can see that phi dash also will be just phi 1 dash etc., direct sum of phi dash t. So, this number of components will be same, and not only that, if this is isomorphic, let us say by pi, okay, that is the isomorphism, that is actually on the Euclidean space induces isomorphism on the root systems. So, then you can see that the pi of phi I as a subroot system inside this phi dash. So, this will be irreducible, and not only that, in particularly, so this has to be equal to one of these phi j dash. Okay. So, that means this pi induces isomorphism between these irreducible components of phi to the irreducible components of phi dash, and since the number of components are same, it just permutes them. Okay. So, now in particularly, since phi pi actually induces isomorphism between one irreducible component to another irreducible component inside phi dash. So, now if you prove that, this implies, so this actually says that phi I is isomorphic to phi j dash. So, then if you prove that the corresponding Lie algebra associated with this root system phi I is isomorphic to the corresponding Lie algebra associated with this phi j dash. So, then you can see that, so this will be one of the ideal. So, this will be isomorphic to G I inside G. So, that way we can prove that G will be isomorphic to G dash, because each simple ideal. So, you have isomorphism for each simple ideal that occur in G and G dash respectively. So, if you put them together, you get isomorphism between G and G dash. So, basically this observation that we have made before reduces our problem to the irreducible case or the simply algebraic case. So, indeed what we need to prove. So, this is again I make it as a theorem. So, we need to prove that if you start with two irreducible root systems. So, let us say phi dash. So, they are irreducible root systems, and assume that phi is isomorphic to phi dash, and phi is coming from the pair G H, and then phi dash is coming from the pair G H dash. So, all these are given. Okay. So, then what we want to prove? Then we want to prove that there exists an isomorphism, from G to G dash. So, note that since phi and phi dash are irreducible, So, that immediately implies G, G dash both are simple Lie algebras, simple Lie algebra. So, this is what we need to prove. Okay. But before proving that, we need to observe something about simple Lie algebras or even semi simple Lie algebras. So, that is observation we will make first, and then later we will use that and then prove this theorem. Okay. So, this theorem now immediately implies var phi is actually injecting. Okay. So, some preparatory work that we need to do, let us do that. Okay. So, for that purpose let us fix only one pair. Okay. You take G H phi. So, this is given as above. Okay. So, that means G is some semi simple Lie algebra, H is a maximal toral subalgebra of G, and then this phi is root system. So, let us say this is given data. Okay. So, proportion is that. So, what one can prove? So, given this root system phi, so which is sitting inside some Euclidean space E, so that Euclidean space is closely related with this maximal toral subalgebra. So, what you can prove? You can actually choose first of all base for this phi. Okay. So, this base is sitting inside this phi. So, then for each alpha inside your base, so you have this root spaces G alpha, G minus alpha. So, these are there. But base has some interesting property. Okay. Given any positive root, you can write combination of that positive root as combination of roots from this base pi, and not only that, you can write this beta in phi plus such a way that you write it as beta equal to alpha 1 plus etcetera plus alpha t, where each alpha I is coming from this pi, and you can also take any partial sum, okay, alpha 1 plus etcetera alpha j, then you can ensure that that is again positive root for all j greater than or equal to 1. Okay. This property is somewhat very important property of this set of base, okay, this base. So, let us use this and then try to understand what it means in terms of the Lie algebra. So, I have already told that means, so G is generated by the root spaces G alpha and G minus alpha for alpha in pi. So, that is what this result means. Okay. So, that is our proposition. So, with all this notation you can prove that, so G is indeed as a Lie algebra generated by G alpha, G minus alpha, where alpha coming from pi. So, that means you can take any non-zero vectors x alpha and y alpha from G alpha, G minus alpha respectively, and those vectors will generate your G. Okay. So, what is the proof? Proof is again just induction on the height of beta with respect to the base pi. So, start with some alpha. Okay. For alpha in pi, so we can choose x alpha in G alpha and then y alpha in G minus alpha, such that this x alpha, y alpha and then the bracket x alpha, y alpha is exactly h alpha. So, this makes SL2 triple. Okay. This makes SL2 triple. So, in particularly you can see that this H alpha is inside G dash. What is G dash? G dash is the right hand side of this equality. So, which is subalgebra of G, which is generated by G alpha, G minus alpha, where alpha coming from pi. We want to claim G dash is exactly equal to G. So, that means, so recall we already have this decomposition of G as root spaces. So, G is nothing but H direct sum G beta, where beta coming from phi. So, to prove that G dash is exactly G, we need to prove that H is there inside G dash and as well as G beta is there for all beta in phi inside G dash. So, let us from this already we can see that bracket H alpha y alpha is bracket x alpha y alpha is H alpha. So, H alpha is inside G dash. So, and this is true for all alpha in pi, but we already know that the span of H alpha where alpha coming from pi is exactly equal to H. So, that means H is subalgebra of G dash. Okay. So, that is immediate. So, now what we do, we take some root space and then show that that root space actually contained in G dash. So, it is enough to show only the positive root space is there, negative root space it will follow in similar way. So, let beta inside phi plus. So, as we observed before, beta can be written as alpha 1 plus etcetera plus alpha t. So, where all these alpha is are coming from pi, and you can also guarantee that the partial sum alpha 1 plus etcetera alpha j, this is again positive root for all j greater than or equal to 1. So, this property is important property. So, now you can see using this property and the following observation, okay, whenever you have alpha dash beta dash inside phi plus, and if you know that alpha dash plus beta dash is again inside phi plus. So, then from this you can guarantee that G alpha dash and G beta dash, the bracket must be exactly G alpha dash plus beta dash. Okay. So, now using this and then using this, so you can conclude easily that G alpha 1 is inside G dash and G alpha 2 is inside G dash, and then that implies the bracket G alpha 1 G alpha 2, which is G alpha 1 plus alpha 2 is inside G dash. So, that is because alpha 1 plus alpha 2 is again a positive root, and similarly G alpha 3 now is inside G dash. So, that implies that the bracket G alpha 3 with the G alpha 1 plus alpha 2, which is G alpha 1 plus alpha 2 plus alpha 3 is inside G dash. So, now using height of beta you can easily conclude that using induction on the height of beta you can easily conclude that G beta is subset of G dash. So, one can prove similarly that G minus beta is also subset of G dash. So, that proves that G is subset of G dash. So, that proves that G is equal to G dash. So, that means G is generated by all this G alpha G minus alpha, where alpha only coming from the base. Okay. So, this is an important observation. Indeed, this observation actually immediately tells you that the Lie algebra G must have some presentation in terms of these generators. Okay. So, that presentation is given by Serre, which is also called Serre's presentation of this semi-simple Lie algebras. So, unfortunately, that is actually uses some ideas from higher algebra, which I can't do it in this course. Okay. So, now let us use this idea and then prove the injectivity of that map that we defined, that is var phi. So, okay. So, what is the theorem? Okay. So, before getting into theorem, let us assume let us see what one gets using the isomorphism between the root systems. Okay. Let us say phi is the root system corresponding to the pair GH, okay, and then you have phi dash. So, that is the root system corresponding to the pair G dash H dash. So, now assume that phi is isomorphic to phi dash, okay, as root systems. So, then what happens? So, that means there exists pi which is from the Euclidean space E to E dash. So, which is an isomorphism, and that also maps this phi to phi dash. So, now recall what is capital E. Capital E is nothing but you take the span of phi over q and then tensor over r over q, that is what capital E. And similarly, E dash is span of phi dash tensor over r over q, everything over q. So, these are the definition of E and E dash. So, now this pi need not be an isometry. Okay. So, that is important point. So, note pi is not necessarily an isometry. So, isometry is something that preserves distance, that means pi of the inner product pi of x, pi of y should be same as the inner product x comma y. This is defined on E, this is defined on E dash, and this may not be true. Okay. This may not be true, but note that if you go back to the axioms of root system, so scaling the inner product does not really affect the axioms. Okay, because the axioms involves only reflections and kata numbers. So, which will not get affected if you replace the inner product by some positive multiple of that inner product. Okay. So, that means by replacing this inner product on E or E dash by some positive multiple does not going to change anything about the root systems. But the thing is, since this phi and phi dash both are actually coming from these simple Lie algebras G and G dash. So, there is a very important observation about the killing forms of this G and G dash. So, basically what one can prove, so this is a fact, so which I am not going to prove it now, actually one can take it as exercise, this is very interesting exercise, maybe I will leave it as exercise. Yeah. So, what is this exercise says? You start with G and then you can see that if you have two non-degenerate bilinear form on G. Okay. So, this G is actually simple Lie algebra. Okay. So, let us say you have two bilinear forms. So, call it beta 1 and beta 2, okay, or maybe we will call it kappa 1, that is what we used. So, the kappa 1, kappa 2, so these two are two non-degenerate symmetric associative bilinear form on G. So, then what one can prove? So, then one can prove that, so they must be proportional. So, then K 1 and K 2 are proportional. So, that means there exists some scalar such that K 1 is multiple of K 2. So, K 1 is some C times K 2 for some scalar C. Okay. So, that is this is only true for simple Lie algebras. Okay. So, note that killing form is one such bilinear form. So, that is non-degenerate symmetric associative bilinear form. So, what this exercise says, killing form is essentially only non-degenerate form on G. If you take any other non-degenerate symmetric associative bilinear form, then that must be multiple of this killing form, that is what this exercise says. Okay. So, now if you go back to the Euclidean space that is associated with the phi, then you can see that the inner product on this capital E. So, that actually induced from the killing form on G. Okay. So, similarly, so on E dash is also the killing form is actually induced from G dash. the inner product on E dash is actually induced from G dash. Okay. So, one can prove that. So, using this information, again I will leave it as exercise. So, the inner product on this capital E and capital E dash, okay, because we have this isomorphism of these root systems, okay. So, that maps phi to phi dash, and both phi and phi dash are irreducible. Okay. So, the ideas are similar to ideas that are used here. Okay. Maybe I will leave it as exercise. You can prove that. So, there exist R positive real number such that the inner product on E and inner product on E dash. So, they are linked using this R. So, that means the inner product on E is just R multiple of the inner product on E dash. So, use the fact phi and phi dash are irreducible root systems, okay, and they are isomorphic, and phi is mapping phi and phi dash isomorphic. So, now using this isomorphism, you can conclude that these two positive definite forms, they are actually multiple of each other. So, now as I remarked earlier, the properties of root systems does not actually change if you take bilinear form and then scale it by some positive real number. So, in particularly we can rescale the bilinear form on E dash, so that we can assume this pi is indeed an isometry. So, there is no harm in it, you modulo this exercise. Okay. So, this exercise allows us to rescale the bilinear form on E dash, and then without loss of generality we can assume, okay, not without loss of generality, with no harm we can assume pi is indeed isometry. So, now since H star is actually spanned by phi, okay, over C, okay, and what you can do, you can fix a base pi inside phi. So, now using this isomorphism pi, you can see that pi of pi, which we call it pi dash. So, that is also base inside phi. So, this is also base inside phi. So, not only that, for example, there is this unique maximal root inside phi. So, that also will be mapped to the unique maximal root inside phi dash. Okay. So, all these properties will be preserved using the isomorphism, there is no harm. So, now you can see that H star is spanned by pi. So, in particularly this pi actually defines an isomorphism between H and H star and H dash star. Okay. So, pi induces an isomorphism between H star and H dash star. So, using the map, okay, pi to this pi dash, alpha goes to alpha dash. So, this is the map that induces isomorphism here. So, now what one can do, so we have this natural identification of H star with H using the killing form. Okay. So, we will use that. So, this already induced map that we have from H star to H dash star. So, let it be there. So, now note that via this map, okay, if you restrict this map to capital E, so then that will be the usual pi, okay, defined on capital E to E dash. Okay. So, we have this natural identification of H with H star and H dash star with H dash via the killing form, respective killing forms, okay, via the respective killing forms. So, now you use this identification and then pull back your induced map, induced isomorphism from H star to H dash star to this pair H H dash. Okay. So, basically you have H and then H dash. So, what we do, you naturally identify H with H star and then H dash with H dash star. So, you have isomorphism here. So, you just pull it back here, so that this diagram commutes, call that map pi. Okay. So, pi is the pullback of pi, okay, using the identifications that we talked before, using the identifications H star and then H dash star, and this is given via the respective killing forms. Okay. So, in particularly if you think about it, so if you take this element alpha here, so then that alpha is mapped to, let us say, pi of alpha here. So, then this alpha naturally corresponds to T alpha inside H. So, then this T alpha will be mapped to some T dash alpha dash, and that T dash alpha dash should corresponds to this pi of alpha, which we can call it alpha dash. Okay. So, that is the correspondence. So, if alpha is mapped to pi of alpha here, then the respective T alpha should be mapped to T dash pi of alpha. Okay. This is same as T dash pi of alpha. So, which is corresponding to pi of alpha here inside H dash star. Okay. So, now more or less we are ready to actually state our main theorem and then its proof. Okay. So, given this isomorphism of root systems actually induces naturally isomorphisms on this Cartan algebras. Okay. So, since H and H dash both are abelian, we can treat this as isomorphism of Lie algebras, no harm in that. So, note that we also assumed pi to be isometry, okay, and recall the definition of H alpha. H alpha is nothing but 2 T alpha divided by alpha alpha. Similarly, H alpha dash will be 2 T dash alpha dash divided by alpha dash alpha dash. Now, since pi is actually isometry, so the inner product alpha alpha will be same as the inner product pi alpha pi alpha. So, if you call pi alpha alpha dash, then this is same as alpha alpha dash. So, that implies if you take pi of H alpha, so then that should map exactly H dash alpha dash. So, where alpha dash is nothing but this pi of alpha. Okay. So, that is how it is all mapped. So, everything is compatible right now. So, you have this T alpha basis. So, that is also there, this H alpha, that is also there, and this compatibilities are there. So, now what we do, given this pi, okay, and this capital pi base, okay, this base is already given. Okay. So, then what we do, we choose let us say alpha in capital pi and then alpha dash inside pi dash, where alpha dash is nothing but pi of alpha. So, you have this root space G alpha. So, what do? You take x inside this G alpha. So, call it x alpha, it is okay. So, you choose x alpha and then you also choose x dash alpha dash inside this g dash alpha dash. So, then you define this pi alpha map from g alpha to this g dash alpha dash, where it sends x alpha to this x dash alpha dash. Since g alpha is one dimensional subspace, you can treat it as a Lie algebra. So, then it means pi alpha is an Lie algebra isomorphism from g alpha to g dash alpha dash. So, now we have actually chosen bunch of maps. So, pi naturally induces map from H to H dash, and we have defined this pi alphas for each alpha in pi. Okay. So, what one can prove? So, given this data, so pi from H to H dash and then this pi alpha from G alpha to G dash alpha dash for all alpha in pi. So, these maps can be extended to G as an isomorphism from G to G dash. Why? Because why one expects something like that? Because G is generated by, we know, G alpha, and if x alpha is chosen, then y alpha is actually uniquely determined inside G minus alpha, such that the bracket x alpha y alpha is H alpha. So, that is why one expects, okay, once these maps are given, then this can be extended, okay, all this pi and pi alpha extends uniquely, okay, pi alpha extends uniquely to one isomorphism from, again we call it G, where we call it pi, from G to G dash. Okay. So, indeed it proves that you all started with isomorphism of these root spaces. Then from this isomorphism, we immediately got isomorphism of Cartan subalgebras. Then from that isomorphism, we have chosen this pi alpha isomorphisms. Then using this data, we are saying that one can get unique isomorphism on G onto G dash. So, that proves our result. Okay. So, now let us guarantee that, okay, this is actually indeed happens. So, let us see how one actually goes about proving this isomorphism. So, this is actually very interesting and non-trivial idea, but once I have shown the idea, it is not that hard to digest. Okay. But first note that G alpha and G minus alpha, they generate G, okay, for all alpha in pi. So, now if you take, so here the remark, so G alpha, G minus alpha, alpha in pi, so it generates G. So, this is the first point. And the second point, so given x alpha inside G alpha, there exists unique y alpha inside G minus alpha, such that the bracket x alpha y alpha is exactly H alpha. Either we have to tell the pair x alpha y alpha, or we have to tell the pair x alpha H alpha. The third element will be uniquely determined, okay, because they form SL2 triple. So, then this 2 observation immediately implies if at all pi exists, that must be unique, because G is generated by this and then x alpha determines y alpha. Okay. So, this implies pi is unique, sorry, the map pi is unique if it exists. So, now let us see how one proves the existence. So, for that purpose, what we will do, so essentially G and G dash are isomorphic. So, then what you do, if G and G dash are isomorphic, then you can take this semi simple Lie algebra G direct sum G. Okay. So, then naturally this G direct sum G will have this diagonal embedding of G inside G. Okay. So, which is naturally isomorphic to G. So, what is this diagonal embedding? So, this is just the x comma x, where x is coming from G. Okay. So, note that this is semi-simple Lie algebra such that this G and G both are this first component and the second component, they are the only simple ideals inside this Lie algebra, and this diagonal embedding of G is actually gives subalgebra inside this. Okay. So, this is somewhat motivates us to consider you take G direct sum G dash and then you construct some subalgebra that looks like this diagonal embedding of G inside G direct sum G. Okay. So, that is what we are going to do. So, we take A to be this G direct sum G dash. So, this is easy to see, this is semi simple Lie algebra as G and G dash both are simple Lie algebras. So, this is semi simple Lie algebra with exactly G and G dash as simple ideals inside G direct sum G dash, okay, where G is identified with this x comma 0 x in G, and similarly G dash is identified with 0 comma y where y in G dash. Okay. So, these both are ideals inside G direct sum G dash, both are simple, easy to see, and from the semi simple Lie algebras theory you can see that these are all the only simple ideals inside this. So, now what you do, you take this D which is like diagonal embedding. So, this is nothing but subalgebra generated by this x alpha bar, where x alpha is given by x alpha bar is given by the tuple x alpha x dash alpha dash, and then this y alpha bar which is given by y alpha dash alpha dash, and then the h alpha, where h alpha is given by h alpha bar is given by h alpha comma h dash alpha dash, and you vary this alpha in pi, okay, and alpha dash inside pi dash, where alpha dash is the pi of alpha. Okay. So, you take subalgebra generated by this, and then this is the subalgebra that we are interested in. So, this more or less behave like the diagonal embedding of G. Okay, let us see why that is true. Our first claim is this is actually indeed proper subalgebra of this G direct sum G dash. Okay, let us assume that and then proceed, and then we will see how one can prove this. So, D must be proper subalgebra of G direct sum G dash. So, how one can prove that? Okay, let us assume this is true. Okay. So, assume that it is true. Okay. So, then how one actually proves our result? Look at the projections. So, you take P1, so which is defined from G direct sum to G given by x comma y goes to x, and then look at P2 which is again defined by G direct sum G dash to G dash where x comma y goes to y. So, these two projections are there. So, then you restrict these projections to capital D. So, then you get a map from D to G, and then similarly map from D to G dash. Now, note that by definition of D, so the projections on first coordinate will contain all the x alphas and y alphas and h alphas. So, that means these projections are non-zero maps and they are onto maps. So, P1 restriction D and P2 restriction D, they are onto Lie algebra homomorphisms, as projections are natural Lie algebra homomorphisms. So, the restriction of that to subalgebra is also natural Lie algebra homomorphism, and by definition of capital D the restrictions are on to Lie algebra homomorphisms. So, what we are going to prove? We are going to prove they are actually isomorphisms. So, for that purpose let us assume that kernel of P1 D is actually non-zero. So, that means P1 restriction D is not injective. So, then that would imply that some 0 comma y will lie inside D for some y inside G dash. Now, note that if this is the case, then what you can do, you can apply repeatedly some add of x dash alpha I dash or y dash alpha I dash on this y, and then since d will be actually invariant under this add of x alpha dash. Okay. So, note that. So, add of 0 comma x alpha dash and add of 0 comma y alpha dash both leave d invariant. Okay. Because this is just from the definition of capital D. Capital E is generated by this x alpha bar, y alpha bar and x alpha bar. So, the add of that whatever it is, it will act on the second part, but it is subalgebra generated by this. So, it will just leave it as invariant. So, that means you can see that if you take add z1 and then compose etc., compose add zs on this y and then take this coordinate. Okay. This must be inside D for all this zi, either this zi is x alpha I dash or y alpha dash where this alpha I dash coming from pi dash. So, this is going to be inside D, but clearly the span of this is also going to be inside D. So, now you can easily see that the span of all these elements, okay, add z1 composition etc., add zs on y where zi is either this x alpha I dash or y dash alpha I dash where alpha I dash coming from pi dash. So, this is going to be exactly g dash. So, because g dash is generated by g dash alpha dash and then g dash minus alpha dash where alpha dash coming from pi dash. So, because of that this generates this. So, that implies that 0 comma g dash is actually subalgebra of this capital D. By symmetry you can easily see that g comma 0 is also subalgebra of D, that forces that D is equal to g direct sum g dash. Okay. But that is not the case, we already assumed this D must be proper inside g direct sum g dash. So, that means this is not true. So, that means the kernel of P1 restricted at D should be 0. Similarly, you can prove that kernel of P2 restricted to D is also 0. So, that implies P1 restriction D and P2 restriction to D both are isomorphic. So, that means D is isomorphic to G and as well as D is isomorphic to G dash. So, then using that isomorphisms you can get G isomorphic to G dash. Okay. So, this is indeed proves that G must be isomorphic to G dash using the map pi, because if you trace back the projections you can see that from G to D and then D to G dash the map is sends x alpha to x alpha dash and y alpha to y alpha x dash alpha dash and then y dash alpha dash. So, that is easy to see. So, basically this isomorphism is given by the map pi. Okay. Okay. We have to prove only the part D is proper inside G direct sum G dash. Yeah, we are running out of time. So, maybe I will do it that in the next class. I will stop here. Thank you.